Good afternoon, and welcome to our third webinar on GNSS Jamming and Spoofing. My name is Rebecca Morrison, and I'm the Senior Director of Standards and Technologies at RTCA, and it is my privilege to be moderating a webinar today on the topic Exploring the Impact of Unreliable GNSS Data in Communications, Flight Decks, and Unexpected Domains. You may be aware that we have done two previous webinars on this topic. The first one was done in May on GNSS Jamming and Spoofing, Building Resilience. So part one had some of our chairs participate in the technologies like TAWS, ADS-B, and required navigational performance on what effect when jamming and spoofing events happened and how they were trying to counter that with our standards. Part two was operational impacts, and that took place in July. Now, if you haven't seen either of those webinars, they are available on our YouTube channel. And of course, this webinar will be available on the YouTube channel after October 27th. So we encourage you to share them with your colleagues or go check them again yourself. And please do email us or contact us if that generates any questions. So today on our webinar, before we get started, I need to give a big shout out to Saffron, who is our webinar sponsor today. We can only do events like this because of our members and our sponsors. So thank you, Saffron, for making this event possible. And what is this event going to be today? Well, I am very happy to tell you that we have 4 expert panelists talking to us about the impacts of unreliable GNSS data, because it could be jamming and it might be spoofing, but there's still an impact on flight decks and in unexpected domains. Joining us today will be Tim Murphy from the Boeing Company, Claire Robinson from Universal Avionics, Mark Klopfenstein from Stein, from Avmat Applications, and Sebastian Chappé from Saffron Electronics and Defense. We will open today by inviting Tim Murphy to join us and give a presentation about the impacts of unreliable GNSS data. And before I turn it over to Tim, I would like to remind everyone that we have a Q&A in this Zoom webinar, and you should feel free to put your questions there. We'll get to as many of them as we can during the webinar. So Tim, if you want to turn on your camera, I'd like to turn it over to you.
Sure. Thanks, Rebecca. I'm here to talk about unreliable GNSS data and why we're seeing impacts in domains that are somewhat unexpected. Next chart, please. So GNSS in general is a large-scale system of systems. I don't think I need to explain it to most of the viewers here. If you're tuned into this, you're probably already interested in GPS and understand how it works. But needless to say, there's many constellations and augmentation signals that come to an airplane. So a rather complicated soup of signals that get received and decoded by a GNSS receiver. GNSS receiver produces position, velocity, and time information. That information is provided to many systems on board an airplane, some of which, the ones here in blue, do some level of anomaly detection and cross-checking with other sensors, which is good. However, those cross-checks were designed for failure detections and not necessarily for spoofing. So there can still be some residual misbehavior in the event of a spoofed signal. Other systems on the airplane don't do as much cross-checking or validity. They'll just believe the GPS position if the GPS sensor says it's good. And that can result in some anomalous behaviors of those systems. And this is not an exhaustive list by any stretch of the imagination. There are many, many systems on board the airplane that use the GPS position, velocity, or time information in one way or another. You'll hear more about those as we go on today. So the good news is the systems in blue, there's obviously a difference between jamming and spoofing. Jamming causes a denial of service, and virtually all of the airplane systems are are designed to expect and respond appropriately to a denial of service. The real difficulties come in when we have a spoofing event and the GNSS receiver is putting out erroneous data, or the GNSS receiver gets corrupted and puts out anomalous data. Some of the downstream systems don't recognize that and misbehave. Some of these systems in blue that do have some cross-checking are pretty good at knowing they're being spoofed, and they'll stop using the GNSS data, but the other systems on the airplane may not. Next chart. So we have bad actors out there doing the jamming and spoofing, and as I've already said, jamming is a denial of service, and the real rub comes in when they're spoofing, because the downstream systems have a lot of trouble dealing with that. Next chart, please. So I've already talked about jamming and spoofing, what that's caused, and I've got a list here of effects that we've seen on airplanes, some of which are quite predictable. You know, you get a degradation when there's just jamming, you get a degradation in your availability of ANP or actual nav performance, and that can even lead to unable RNP. Again, those are normal responses to a denial of service. But when we get into spoofing, you get all these other effects. The spoofing can cause erroneous hybrid positions because the hybrid corrections of the inertials get corrupted by the erroneous GNSS data. We can get spurious alerts from a number of systems. Enhanced ground procs is probably one of the most disruptive that we've had so far, but also our runway overrun monitors and the RAS monitors are all susceptible to either false alerts or unavailability, and that can be disruptive in an operation for a number of reasons. The other thing that can happen in spoofing is you can get a date or time shift, a time of day or date shift, and lots of downstream systems don't know how to deal with that, or don't deal with it well. Later, one of the other panelists will talk about the impact of that on datalinks, but it's really it's a problem for many things. For example, the maintenance systems on the airplane are time stamping everything, and if they're time stamping it with the wrong stamp, then all of the downstream systems on the ground that consume that data have problems. So I think that's all for this chart. Next chart. This is a map that just shows the extent of the problem. This heat map was developed based on real data collected with maintenance systems on board the aircraft. We have a system we've developed called the GPS Event Monitor, which uses a system on board the airplane called ACMF, the Aircraft Condition Monitoring Function. And we've programmed triggers and algorithms to detect and log when interference or spoofing is seen. And then we'll actually compose an ACARS message and send it to the airline and to us. So we get automated reports of jamming and spoofing events, and we've been collecting those for now close to a year, and we've literally got thousands and thousands of these approaches. And it's quite nice because we can see when and where these spoofing and jamming events are happening. We can tell the difference between the jamming and a spoofing event of various kinds. So we can collect statistics, and we can decide which are the most important problems to go fix first. But also we can advise our airline customers as to what kind of jamming and spoofing they may see in different regions. But one of the main takeaways I want you to have from this chart is over on the right-hand column, there's a list of the FIRs and the number of aircraft, or the percentage of aircraft that fly through those FIRs that had some level of jamming and spoofing detected. So At this particular reporting interval, we were seeing 77% of the airplanes that were flying through Ankara were jammed and spoofed. So this is not a small problem. It's a daily occurrence in many areas of the world, and a serious issue. This automated reporting is great. We love it. We felt like we had to do this because we figured out early on that pilots won't report. They'll report it the first 10 times they see it, but if it's a daily occurrence, they're not going to fill out a report. So we had to develop this automated reporting system. Next chart. So from our perspective, we think we need multiple layers of mitigations here, starting with operational mitigations. Airline operators need to understand the impacts of jamming and spoofing and what to expect in the flight deck. And then ANSPs need to disseminate information about jamming and spoofing so that airlines can be prepared. We can also rely on toughening the GNSS system at the source through cryptographic means of authentication at the satellites. That's all underway in standards development. But the bad news is it's going to take a long time for that to be there, and it's only partially effective against spoofing. Then there are mitigations at the antenna level. We've probably all heard of SERPAs. Those are really just at the beginning of the standards development process that's needed for a commercial application. But the good news is the SERPAs were recently taken off of the ITAR or the munitions list, so they're exportable, potentially exportable. So that opens the door for civil applications. So there's lots of different things, and I think Sebastian later will talk about how to toughen GNSS receivers, and then toughening at the airplane level through improved sensor fusion. I think Sebastian will also talk about that a bit. So next chart. So the bottom line from an OEM's perspective is that we need these multiple layers. We need them all. There's no one silver bullet here that completely solves the problem. And even with everything we can throw at this problem, there's really a limit to how robust GNSS can be made. So reversion to alternative sources of navigation will always be a part of the solution. And there's a lot of focus in the industry right now talking about resilient operational networks and how to decide which conventional nav aids you need to retain. There's also a lot of talk going on about developing improved complementary PNT systems. That will take a while, but I think it's important as we move forward to be thinking ahead. And then finally, one of the things that this crisis that we've been going through with GNSS spoofing has shown us is just how dependent we are on time synchronization. It's been taken for granted. It comes so naturally and easily from having GNSS. We just started using it everywhere, and now we didn't really pay enough attention to how critical is the time synchronization and what can be the impacts if an airplane is not synchronized properly in time. And there's talk in the industry and work starting up at ICAO to go through and now try to put some requirements around, for example, time integrity, time synchronization integrity. I think that's my last chart.
So Tim, thank you so much for that overview. There's so much about aviation and avionics systems that has that dependency on the timing and the position information. And I really appreciate your expertise in laying that out for everyone on some of the places you didn't know weren't going to work when a jamming or spoofing event takes place. I did have a follow-up question for you. You mentioned that it affects the maintenance data, which gets collected on aircraft and is so important to keep our skies safe and our aircrafts robust and operating. Can you say any more about what happened? Like, is the maintenance data usable after an event? And did that inform updates to your tool on automatic reporting?
So spoofing can impact maintenance and operational maintenance in a number of ways, not the least of which some of our sensors, when they're spoofed in certain ways, require maintenance action to be reset so that they'll work again. In fact, there's a couple of part numbers and different types of spoofing where if they experience that spoofing, they won't work for the rest of the flight. And they might work when you recycle the power. And there are some older receivers that literally need to go back to the shop to have their non-volatile memory reset. We're getting those out of the system as fast as we can and replacing them with receivers that are and software updates to receivers that are more robust. So that's one impact on maintenance. It actually adds to the maintenance that the airline needs to do. But the other impact is the fact that everything is time-stamped. So once you skew that, sure, theoretically you can go in and correct it if you can synthesize a different clock somehow and correct the data. But generally speaking, I think you would just lose that data.
That is good to know. Although, as you said, it's evolving, and how many events have happened over the last year. I know they're getting more, so we'll learn more the more events we have, right?
Yeah, yeah. We rely on our airline operators to report when they see something new in the cockpit, and then we work with them to analyze that and then program that into our maintenance data so we can collect information about how often it happens, where it's happening, and so forth. So our automated reporting is going to evolve as the threats evolve.
Thank you so much for that, for all the
Sure.
information you've given us today, Tim. And don't go away because I want you to come back for our panel Q&A session. But right now, I'd like to invite Claire Robinson from Universal Avionics to turn on her camera and join us. And as Tim alluded to, Claire's going to talk to us a little bit about how GNSS spoofing impacts on data link applications. And before you start, Claire, I want to tell you it was during our May webinar when someone asked me, well, why aren't you talking about that you can't use data links? And I was like, what? So please educate me and everyone else about what we're talking about that GNSS spoofing affects our data link operations.
Thanks, Rebecca. Yeah, the GNSS spoofing has been a big topic at recent data link forums, which I think has surprised people, but I'll take us through some of those impacts here. So as Rebecca said, I'm Claire Robinson, and I chair SC214, which is the RTCA committee handling ATS data link applications. So just a quick overview of the different applications in use. We have ATN B1, CPDLC, which is the controller pilot data link communication, which is used in continental European airspace. That's been in use for a long time. CPDLC is that text-based communication directly between the pilot and the controller. We also have ATS B2 CPDLC and also ADSC, which is the automatic dependent surveillance contract. That's more of a surveillance-based communication. The ground requests certain information from the aircraft, and then the aircraft provides it at the rate requested. So B2 ADSC is being used in some European airspaces now, but it will be widely used beginning in 2028 to meet the forthcoming mandate for that. And then we also have FANS 1A+, which is CPDLC and ADSC, and that's used globally in a variety of different situations. For example, in the North Atlantic, they use both FANS, CPDLC, and ADSC. In the domestic US airspace, they're using CPDLC and only using ADSC in the oceanic, but FANS is being used everywhere in Australia, Japan, Singapore, etc. So it really is a global application. You can go to the next slide. So the GPS spoofing impacts on CPDLC, as Tim alluded to, really come from the time synchronization issues. So I've broken it out into the various behaviors, for example, when you're trying to log on just to start using the system versus once you're already logged on, what the impacts are. So with ATN B1 and ATS B2, if your aircraft is experiencing spoofing and you attempt to log on, the logon will just fail. It will be rejected due to the time synchronization issue. And that's built into the protocol. So there's not really much we can do to work around that without creating a new protocol. For FANS 1A plus, the time synchronization is less important. So you will be able to successfully log on and then use the system. And then once you are logged on, if you are receiving an uplink, again with B1 and B2, if that uplink is in the future or older than the latency time that's set, that message will be rejected by the aircraft system, and the crew will see an error and they won't be able to see the message. And then additionally, position-related data may just be incorrect in any of the messages exchanged. In FANS, it's a little bit different. They have a latency timer, which is not used everywhere. So it depends on if the ground system is choosing to use the latency timer. And then there are also some differences based on the platform. So some systems, if an uplink is received that's older than the allowed latency, it might just reject it and not display it to the crew. And others will still display it, but have an error message on it saying this message is old. When the aircraft is sending a downlink, the ground system for B1 and B2 will reject the message. And in some cases, that will cause the ground system to abort the connection. And I know people are familiar with the provider abort issues. This can lead to more aborts if the time is out of sync. And with FANS, it's more based on the local policies. Some ATSUs will continue using the messages and others will display them with an error similar to on the aircraft. We can go to the next slide. So then similarly with ADSC, there's no impact on B1 since B1 only uses CPDLC. But the ground will be able to establish the contract with the aircraft, requesting, for example, current aircraft position data that's included with every report, projected data for future waypoints in the flight plan and ETAs, etc. But if the aircraft is experiencing spoofing, you can't trust the data that's in that ADSC report. So the aircraft position and time may be inaccurate by varying amounts, and then any projected profile information that's built from that may be wrong, and that applies to both B2 and FANS. So that's a high-level look at the impacts on the data link applications, and I believe that is the last slide there. Go to the next slide. Yes.
Thank you so much for that, Claire. Like I said, I was shocked to learn that data link did not function perfectly in the events of jamming and spoofing. And I actually have two questions for you right now that maybe some of our audience members would also think about. You talked about the impact on the communication between ground and air, between the pilot and the air traffic controller operations. But is there a larger operational impact that might happen when you lose the ability to data link that you can talk about?
Absolutely, yeah. So for example, with B1 CPDLC, there are operating rules that the pilot has to log on when in certain airspaces. For example, in Swiss airspace, you have to log on. So if that log on is getting rejected and the aircraft isn't logged on, that aircraft may not be able to fly above flight level 285 or make it less desirable flight levels. Similarly, any aircraft entering the North Atlantic, they are required to have FANS capability for the preferred routes. And so aircraft that are coming from areas where spoofing is going on, the controllers in, for example, England, they don't know if the aircraft coming in are experiencing spoofing or not. And so they may just have to default to saying, okay, these aircraft that are coming from high spoofing areas get less preferred routes. So there is a cost to that and a time impact on flights. And especially if the pilot isn't aware if they are being spoofed or not, then there's no way to say, oh, it's okay, my aircraft didn't get spoofed, I should still get the preferred route.
Yeah, and I know none of us want to be on the plane that suddenly gets the non-preferred route, and we're arriving in 5 hours and suddenly we're arriving in 7, right? On those long cross-ocean journeys, which I just came back from one. I do have another question for you, because you mentioned the only way to address would be to write a new protocol. And I know you've been chair of 214, which RTCA thanks you very much for several years. If we were to start writing a new protocol, can you give the audience, our attendees, an idea of how long that takes? I mean, you'll have it next year, right?
I think you'll get the GNSS mitigations before you get the new protocol. So
Okay.
I would focus on that at this point. It's a long process, and we're rolling out B2, and that time synchronization is inherently an inherent part of that protocol. And so changing that would be a massive overhaul. Even just changing it within the existing one, I think would take several years and a recalibration of operation, because that's part of how, both pilots and controllers know they can trust the messages they're getting, because there's that time synchronization. You don't want to respond to a clearance that you got over CPDLC if you don't know that it's fresh. So the time synchronization, we're learning, is a potential issue with this GNSS spoofing, but it's also necessary for trusting the data that you're getting.
Thank you for that, and for giving us more insight into some of those choices that you've made, that maybe it makes you vulnerable to jamming, but there's a reason you made that choice. So thanks so much. Now we would like to turn to Sebastian Chappé from Safran Electronics and Defense. Sebastian is going to give us some information about some of the resilience that Safran has integrated into their products using positioning, navigation, and timing, or PNT. So Sebastian, please help us understand more about what can be done and what you have done to address these issues.
Thank you, Rebecca. I'm going to introduce you with resilient position and timing. First slide, please. So GNSS was a wonderful source of position and time for many years. It was available, accurate, and cheap, and it was combined with inertia to cope with short-term unavailability or simple satellite failures. The principle was GNSS-centric, and every time there was a GNSS signal, it was taken into account as a reference for the system. In case of anomaly, the pilots were often thinking that the inertial reference system was probably misfunctioning. These days are over, and the chart that Tim showed is compelling. GNSS can no longer be trusted 100%. As a consequence, the whole navigation concept with GNSS and inertia coupling has to evolve to resilient position, navigation, and timing. Next slide, please. So let me introduce you with two examples of RFI consequences that we faced this year. So first, within Safran, we purchased the UAV from an external source, and we did some experiments there on the field with some time spoofing attack. The time spoofing attack that we did on the UAV caused actually worked, even if the UAV was labeled as GNSS denied ready, and the avionics had a major disruption, and in the end it fell on the floor, proving that even labeled GNSS denied ready, this type of attack is not simple to handle. On the commercial side, we have also some reports from some aircraft that experienced some spoofing events, and the data within the inertial reference system got corrupted within the Kalman filters, and it resulted in the end with a misapproach at landing phase. Next slide, please. So from Safran perspective, we are facing two paradigm shifts. The first one is that the GNSS can no longer be trusted. It's an unprotected cyber backdoor, and the question is not if you will get spoofed, but when you will get spoofed. And even Galileo OSNMA with authentication on the ephemerates does not cover every spoofing attacks. The second paradigm is that time and synchronization were undervalued assets. And now the industry has to find new ways to get the synchronization on board aircraft between equipments, between aircrafts and ATCs and operators. In Safran perspective, the goal for the industry is now to ensure the safe travel within the RNP bands without GNSS, even without GNSS. Next slide, please. So how do we translate this? For availability, integrity, and accuracy of PNT data, we implement a resilient PNT approach with multi-layered approach based on a PNT core that needs to be protected. It is composed of fully immune and autonomous sensors, the clocks, the gyroscopes, the accelerometers, protected by identification, detection, mitigation algorithm, and with layers of protection depending on the use case. Either by robustifying the GNSS acquisition, using multi-sensor fusion, and also using some alternative PNT sources. Depending on the use case, the sensors of the platform, the budget, the performance looked for, we apply one or more countermeasures. Next slide, please. So today I'm going to focus on 3 countermeasures: the anti-jamming antenna, the IDM algorithm, and the PNT core. Next slide. So the PNT core, this can take the form of an attitude and heading reference system, an inertial reference system, a holdover clock. This is the North Star of the system. This is the PNT safety net when the GNSS is under attack. This type of sensors bring predictable performance. The DARPA did some assessment a couple years ago on different types of gyroscope, and the hemispheric resonating gyro from Safran went ahead of its game on the performance and SWAPC for navigation grade the inertia. We have been investing actually a lot for 20 years on this gyroscope, and this is now phasing out the ring laser gyro. We have more than 60 million working hours without any failure. From Safran perspective, this brings the confidence for the pilots to believe in the inertia against GNSS. We also bring a new innovative design with double IMU that brings the inertial performance a decade above, a decade better. On the timing side, there is also proven solutions like rubidium or cesium clock that can become the safeguard of time on board the aircraft. This is actually 5 by 5 by 2 centimeters, and this can typically hold 1 microsecond delay for holdover of 24 hours. Next slide, please. Now let me introduce with identification, detection, mitigation. In order to protect the PNT core, this algorithm detects the abnormal GNSS signal. We distinguish 3 main types of IDMs. The first one is inertial IDM. Inertial IDM is based on inertial sensor data that detect and filter corrupt signals. To give you an example, we could use 3 sigma test to reject erroneous measures, or also reject GNSS position that are above the recorded bias of the sensors. For time IDM, this is a little bit the same principle with a clock that is used as a sensor. For both inertial and time, the quality of the sensor will result in the quality of the anti-spoofing method. The open IDM is a little bit different. It's about a compilation of 70 different algorithms tailored to a GNSS receiver in order to detect abnormal signals with over 98% probability. These algorithms have been implemented in a spoofing detector actually used by US soldiers that you can see on the screen, the broad sense, that triggers warning when the spoofing is encountered. Safran is currently working on a solution tailored for the pilots on board aircrafts. Next slide, please. For robustifying GNSS, an innovation incoming are the control radiated pattern antenna. CRPA dynamically generates one or more special nulls in an antenna array by signal processing in time or in frequency. Their job is to reduce the denial radius of the jammers. And there is actually a working group within RTCA to set up the regulation in collaboration with RTCA in order to bring this innovation on board the aircrafts. For accredited users, there is also encrypted signals such as Galileo PRS that are coming very soon. These encrypted signals provide built-in anti-jamming and anti-spoofing features that can be fully trusted. Initial operational capability of Galileo PRS will be declared in the upcoming month as Safran has flight-proven solutions that are modernizing more and more aircraft fleets in Europe and its allies. Thank you.
Thank you so much for that, Sebastian. That was super interesting, understanding now that we have to deal with GNSS jamming and spoofing, that there are things that can be done to enhance the signal and reduce the impact on operations. I think you mentioned that you believe that 98% of the events that happen of jamming and spoofing are detected. Can you maybe tell our audience a little bit more about where that number of 98% comes from and how you've changed the detection over time to increase your success rate in detecting events?
Yeah, thank you very much, Rebecca, for this question. Actually, within Safran, we consider that GNSS spoofing is an ever-evolving field, and so we need to be constantly on top of what is happening out there. And so we have set up over the years a library of the spoofing attacks based on what we record in the field, but also what we can simulate within our business unit of GNSS simulators. And so we have built actually a library of over 9,000 type of attacks that we can run through our algorithm to provide some computation and these types of probability.
Thank you so much for that. And again, no one go away because we want you to come back to participate in the Q&A, Sebastian, but we have one more presenter today, and that is going to be Mark. Mark from AVMET is going to, Mark Kloffenstein, Stein. Mark, thank you so much, and please forgive me for not learning it better. Mark's going to talk to us a little bit about another thing I discovered when I was researching for this webinar. I had no idea that GNSS jamming and spoofing could have any effect on the weather other than to cause thunderstorms. But Mark's going to tell us a little bit about what the effects really are and what can be done about it. So welcome, Mark. Thank you for joining.
Thanks, Rebecca, and good afternoon, folks. I want to talk a little bit about one of the unexpected domains, other than kind of where are the aircraft, and it's the weather domain, and not so much the direct impact on the weather itself, but our ability to observe and forecast that weather. It's not just for navigation. We get a lot of real-time, high-resolution data from just the signals coming out of the satellites and how they travel through the Earth down to the, or travel through the airspace down to the Earth and to other satellites and stuff like that. And if we experience problems with the data, such as jamming and spoofing and other outages that might cause, this could affect both the cockpit decision-making, but also ground-based forecast accuracy. So next slide, please. So let's talk a little bit about what's going on in the aircraft itself. So the aircraft has its own weather radar, looking, forward and downward, trying to make sure that it has a safe path to go through the airspace. And having a precise geolocation from the GNSS system helps to tag these radar returns with the accurate position and the altitude. The timing synchronization is really important for, looking at the Doppler sweeps and the velocity measurements and the pulse coordination and some of the, details of kind of getting an accurate radar display on the pilot's screen. Not only that, but there is the position information, which is important because it helps to sync up the other data that the pilot's looking at, things about the flight path, the terrain avoidance, and things like that. And all this data is being fused together for information support for the pilot. Things like ADS-B getting added in, terrain awareness, warning systems, and other systems that are all promoting situational awareness for the pilots. So if these things, get degraded due to GNS on the next slide, radar misalignment, data drift, that could cause the aircraft to miscalculate its position, which would then potentially cause weather cells to appear displaced from where they really are or where the aircraft is relative to that. So you get into decision making about how am I going to route myself around the weather. If you don't know where the weather is, you could potentially route yourself into the weather. Timing errors, timing drift, also degrading these Doppler velocity measurements. Also will have an impact of potentially reducing the radar coherence. So you get more of a blob of weather as opposed to a well-defined boundary to that. Certainly, we're really concerned about false terrain and weather alerts, from that type of perspective, and other problems with the flight management system anomalies that you could get, because that could really, if you get a lot of false returns, the pilot's going to start dismissing the information, become potentially desensitized to a real alert, and hopefully nothing would happen from that perspective. But let me next pivot to a broader view of how GNS information supports weather forecasting on the next slide. So we do a lot of atmospheric profiling via GNSS radio occultation. So this is a technique where a signal coming off a satellite, will bend in the Earth's atmosphere, and then you can measure the degree of that bending with other satellites or ground sensors. Another technique is to look at the signal delay. Since it's a very accurate clock, you can get a measurement of the delay through the atmosphere. And this allows us to come up with very precise profiles of the temperature, pressure, and humidity within a column of air. The timing and synchronization is very important, pulling together the Doppler sweeps of existing ground-based radar looking at the weather with the satellite type data, and geolocation of mobile sensors. So we do have a couple systems, TAMDAR and AMDAR, for example, that are weather-based weather sensors. So all the aircraft that are participating, gather weather data information, and it's all time and location tagged, which is then uploaded into the numerical weather models by NOAA and other weather providers. And it's really important that you're getting accurate data from a point of reference of when and where were these measurements taking place, particularly when you're looking at the tracking of precipitation and the potential for precipitation, which is really the raw data necessary to look at some of the short-term movement and boundaries of thunderstorms, which are particularly a problem for aircraft trying to avoid that. And other mobile sensor networks, you got ships out in the ocean that are participating, looking at the GPS signals, contributing that to the weather networks. Also sensors of buoys, weather balloons, other platforms. These are all collated together and tagged using the GNSS system. So on the next slide, if we disrupt some of this data, outages, obviously, loss of some of these atmospheric profiles, there's only so many weather balloons that can go up. The satellites really help looking at remote areas, areas across the ocean, and other things like that. Certainly the timing drift is going to cause model forecasts to be ingested that are going to be corrupt and hard to reconcile with other data systems. And one of the problems with the weather ingest, once we ingest the bad data, that's going to persist, for potentially several hours, when you're looking at a fusion of forecast information, trying to project out, some just in the short term for weather avoidance of an aircraft, but also sometimes when we're looking at the general ground delay programs and rerouting and overall traffic flow management, is required to know where is the weather or where potentially the weather's going to be. Spoofing is going to potentially cause even worse problems where you put storms in the wrong location at the wrong time, and that could lead to maybe not so much safety issues, but certainly inefficiency issues when you're talking about reroutes that are putting planes into the wrong location, filling up nat tracks where now a track, flights trying to request to go to a different track, things like that. So it is a safety risk, but it's also an efficiency risk. So hopefully that just gives you a little bit of an idea of some of the unexpected domains that spoofing and outages in GNSS system could cause. And with that, I think that's my slides. Thank you.
Thank you so much for that, Mark. Like I said, I discovered this as we were researching the webinar, and we really appreciate yours and everyone's participation in the webinar today. I will ask you a follow-up question, and I think I want to hear a little bit more about the impact on efficiencies. We are in the aviation community so dedicated to safety, and that's absolutely number one. We don't always talk about the inefficiencies that also impact us that we have to combat to be able to maintain safety. So do you have an anecdote or a perspective on how these inefficiencies have further impacts, or something that you've been told on why we need to reduce them?
Right. Yeah. So a lot of what we do at my company is try to better determine where the weather is and where the weather isn't. And so anything that helps improve that potentially allows us to open up additional lanes of traffic when we have these days where you have, a large storm front, but there's holes in the weather. So we can route traffic through there. And just a little bit of extra permeability through the airspace in a convective weather event will allow 2 or 3 more aircraft to go through per 15 minutes, which really can magnify or de-escalate the amount of delay. Because when you look at, say, the New York market, where you have 3, 4 busy airports and all the US traffic trying to funnel in and out of that area, you put a storm in the wrong place, it could disrupt the entire NAS. There's this propagation effect. Once one flight is delayed, then it lands late, and then it's going to be late going back out. And so you have some of these days that are really the traffic controllers will throw their hands up, and we're talking thousands, tens of thousands minutes of delay, where a little bit of improvement, particularly early on in the day, could have mitigated a lot of delay. So yeah, it's really important, and certainly intentional loss of data, like through spoofing, is a concern. And just like you guys didn't know that weather is relying on this data, I don't think the weather folks are realizing that spoofing is happening and something that they need to worry about in their data ingest. So that's another issue.
Thank you so much for that. That it really has highlighted how all of the systems, GNSS is a system of systems, but then all of the systems are integrated together to maintain not just safety, but also efficiency. But now I know who to call when I'm on the tarmac, right? To get I'm just kidding. So I thank you again, but I would like to invite all of our panelists back. Tim, Sebastian, Claire, if you could join Mark and I online, because we have some Q&A for you. And I would like to invite all of the audience, if you still have more questions, to send them to us, because we've got about seven minutes left, and I've been asking my questions all along. I'm actually going to start with one for Claire that is about the CPLDC fans 1A plus. But then there's two questions for you because they also wanted to ask about CPDLC and fans. The first one is, are the same errors that happen from a jamming and spoofing event that's identified on the aircraft, are they identically available or happen on the ground?
Right. So in fans, if you are implementing the latency timer, that's only on the aircraft. So the aircraft has a specific delay time set by the ground. And then, as I mentioned earlier, the way that's displayed is different on different aircraft platforms. On the ground, there are higher level safety requirements indicating that you should alert the controller if a message is delayed, but it is more of a local implementation decision on how to let the controller handle that. So some systems choose to handle it a little bit differently depending on their airspace use cases.
Thank you for that. And then the second question related was, is there any work in incorporating frequency hopping into the data link like they have in some systems that aren't for commercial use?
I'm not aware of any work in that. I don't think it would address the issues with spoofing that we see at the application layer. The data link applications get the time and position data, either from the GPS system directly or maybe through the FMS, but the data link application is not necessarily responsible for making sure that data is valid. So it's coming from a trusted system. And so I think having the mitigation at the source would be more effective there. But the frequency hopping wouldn't work in the current data link environment.
That's that new protocol that you'll have out next year for us, right?
Yes.
No, but it's a good question because we do hear solutions in other applications and we want to plug them in. So I'm going to combine a couple of questions for Tim and Sebastian and talk about it more generally. Tim, you talked about the database of reporting that you get back from your fleet now and pulling it together. And Sebastian, you talked about the database that Safran has maintained. Is there a worldwide or even US only database where these events are getting reported that is becoming public domain or data access so that everyone has access to them? Or is there a desire to do that, given that jamming and spoofing pretty much means there's a bad actor happening? Tim or Sebastian, either one of you can jump in on that if you're willing to.
From my knowledge, there has been some work from the GRC, so linked to the European Commission, to define some spoofing and jamming scenarios that has been shared within EuroCAE and I think RTCA. From Safran work, we are also working on defining jamming and spoofing GNSS scenario to help improve the GNSS receivers publicly.
Thanks. Tim, did you want to weigh in?
Yeah, the FAA does have a reporting program, but it's based on pilots actually doing it. There are other commercial services that are trying to observe and measure the extent of GPS RFI through things like space-based ADSB or ADSB in general, inferring that apparent outages are real RFI events. And those are interesting. I've sat through briefings at the P&T advisory board where the Department of Transportation had a program to try to fuse all kinds of information like this into a central source. But frankly, I'm not up to speed on the current status of that.
Thank you for that, finding out about it. Maybe it's something that can evolve in the future. This is a very interesting question that just popped up, which is, we mentioned aircraft systems detecting spoofing and jamming and understanding the events, but are there any ground systems available to controllers or ANSP to detect the spoofing and jamming event at this time that you guys know of?
Yes. There are a couple of commercial vendors. I don't know if I need to give them free advertising in this webinar or not, but yeah, you can buy ground-based equipment that's intended to detect RFI and spoofing and locate, for that matter.
Actually, what I showed today for aircrafts, especially the broad sense and the spoofing detector, can be used also on the ground. And there are also the LDM algorithm that were shown are also implemented in the time servers that are used all over the US and Europe.
Thank you very much for that. Just want to, okay, if I wasn't able to get to your question today from the audience, we will try and get questions answered from our panelists and provide the information to you. But I would just really like to thank Tim Murphy from Boeing, Claire Robinson from Universal, Sebastian Chappé from Safran, and Mark Klopfenstein from Avnet Applications for your participation today. Not only can we not do these webinars without our sponsors, but we cannot do them without our members participating and sharing your knowledge of the aviation industry and our impact, that what we do has an impact there. So thank you so much. And if you have other questions, the chat remains open and we will pass them along to our panelists after the today. So thanks again, guys, for joining.
Thank you.
Thank you very much.
Before we go, I'm looking for my slides to come back. Here we come. I want to remind you that this webinar will be available on YouTube by October 27th, and that parts 1 and parts 2 are already available on YouTube, and those parts informed this one. So please go ahead and give us, take a look at how our conversation evolved. Another great shout out to Safran for being our webinar sponsor today. We could not do this without our webinar sponsors and our members. So thank you very much, Safran, for your time today. I also wanted to let you know about another activity we have at RTCA that might be of interest to you. We have training courses and they happen about quarterly. And this December, you can get training in 3 of our many foundational standards. The first week of December, we will be training on our software process documents with DO-178C and the supporting supplements. The second week, you can go to NIAR for in-person training, where not only can you get training on how to do DO-160 environmental tests, there are going to be demonstration tests run for the participants of this training, and it's great to see people get back into in-person training events. And then you can, finish up your Christmas shopping by also attending our design assurance training for DO-254. It is in some ways like 178 is for software, DO-254 is for hardware design. And if you need more information about that, that's at rtca.org/training. And finally, I just want to thank all of you for joining us. We can't do these webinars unless you let us know what you like, what you don't like. So please fill out the survey that you'll receive it after this webinar. But we hope you enjoyed it today, and we thank you for your time and attention. Have a great afternoon. Bye.